Thank you, Martin. I'm super excited to be here. I got to spend a year with my Czech friends, and I've never been to Prague before, so this is my first time here, so thank you for having me. I want to talk about DeepStack, but before I get started, I want to say that this is a project that involved a great team of people, one of the best team of people I've gotten to work with, and of course, you know many of the instrumental members of that team are, in fact, from here. Thanks very much for their involvement, and really, they should be giving this presentation because this is a celebration of their work, but you're going to hear it from me instead. Hopefully, you'll get to hear it from them as well, too. To get started, to understand DeepStack, actually, we need to understand a little bit of history of AI, because the story of DeepStack is really a long-running story of artificial intelligence, computer science, and how those interweave with games. Because games have always been around from the very, very beginnings of thinking about artificial intelligence. And so while it's 2017, we've seen many breakthroughs recently when we've thought about games, right? We don't have to go back very far to just last year where we saw AlphaGo defeat Lee Sedol. And Go had been a long-standing challenge problem, often seen to be 50 years away from where our AI techniques were even a decade ago. And now we're able to conquer that game. We might want to look back, though, 10 years ago from today, where we saw another very interesting games result, where we had a computer program solve the game of checkers. So this involves actually producing a perfect strategy to the game, so that it can't be beat no matter who it plays against, because it actually guarantees that it will always tie. And if the human it's playing against makes a mistake, which humans are prone to do, then it's going to actually win the game. But of course, we really, if you think about sort of the landmark event, when we think about AI in games, we have to go back another decade before that to Deep Blue defeating Kasparov at the game of chess. Chess, again, was established as one of these paragons of what human intelligence can achieve. And in 1997, we saw we could get computers to reason through in that game as well, too. Now, I always like to bring up that maybe we should go back just a few years before that, where we had a program done at the University of Alberta called Chinook, done by Jonathan Schaefer, that actually was the first program that defeated a world champion at a game that humans play. And that was in the game of checkers, where Chinook defeated Marion Tinsley. But maybe you're old school and you don't even think into the 90s, and you want to think way back, because computers and games and AI go way back. Right? And we can go back to Turing and Shannon, where both of these seminal researchers in computer science and in AI actually wrote computer programs to play the game of chess. And in Turing's case, he didn't even have a computer to actually execute his program. So he actually by hand ran his program and actually played a game of chess against a chess player to sort of prove that you could get reasoning in these games. But maybe you want to go back further than that, and we can go back to before we even had computers, and we started thinking about computation as a way to getting to intelligence, and we have von Neumann sort of thinking about how would we reason about, how does the mathematics of games work so that we could actually understand what the right moves to make are. And so that was a big piece of the work of development of game theory, which is an area that he worked in before he finally decided maybe I need computers to make my theory work. But we can go back even further than that, long before we actually even thought that computers were a thing, where we have Ada Lovelace and Charles Babbage. We have in Babbage's journal, we can see schematics for an automaton to play tic-tac-toe. They dreamed that the analytic engine would eventually be able to play a game of chess. So at the very, very beginnings of us having computation, we were thinking about computation as it relates to intelligence, and then we were using games to try to understand that. And so this goes way, way back. But why has computing and AI been so connected to games? Because we often think about games as being this childish plaything. These aren't really like important people. We do important things. We study important problems, and games aren't those. Those are things for kids. We study things like we become doctors and engineers, and we build bridges, and we operate on people, and we don't do games, right? But at the same time, we have our children play games. And I don't think we do this just because we want to get them out of our hair. There are many reasons why it's a good thing for our children to play games. And it's because of what games can teach us. If you think about what games can introduce to our children about how the world works, very, very early games teach concepts like colors and numbers and pattern matching. As they get to more complex games, they can see their actions have effect on the world and change how the game is going to play out. And then they can plan to try to achieve effects. Oh, I want to get here, so I need to take these actions to do so. Or they can have long-term plans about how they're going to actually, reach the end of the game. They also learn strategic thinking and problem-solving skills. How do I overcome a challenge that they're facing? They also have to handle cooperation, so there's other players in the game, and how do they interact with them? And they need social skills, so they can learn how to be good winners and not poor losers. All of this they learn as they sit down and play these short little games. But there's other reasons why they get this. They get this because there is a very short time frame for which you get feedback. So in our everyday life, and we make a mistake about like what we're going to study in university, we might not discover that mistake for 6 or 7 years, and then 15 years later, we're like, oh, I can't believe I made that mistake. That's really unhelpful for us trying to train our processes to make decisions, right? If it takes 10 years to discover a mistake. Whereas in these games, we get the answer in like 15 minutes or a half an hour. We find out, oh, that wasn't a good path. Maybe I should change how I think about these kinds of games. But also, we have very low consequences to our choices in games. Right? Like, if I'm going to be a doctor and I'm going to operate on somebody, then a mistake here is very costly. Where a mistake in a game, if I'm playing the game of operation, where you have to try to pull little bones out without running the buzzer, that doesn't cost me anything. I just get buzzed. So games have low consequences, quick responses to giving us feedback, and so what they act as is the perfect example of a proving ground, a place that you get to try out your ideas, a place that you get to use your skills and develop them before you go off in the real world and do really important things. Okay, but this talk is about AI, but if we think about what we want our AI to do, what do we want it to do in the world, how do we want it to act, well, all the qualities, all the skills we want it to have are in fact the same qualities that we want our children to develop as they grow up. We want them to be able to understand colors and numbers and pattern matching and short-term and long-term planning and critical thinking and being able to interact with other agents in the world and other humans. And if we're going to want our AI to do this, just like with our children, we're going to need them to have a proving ground, a place where they have low consequences to their actions, but also quick feedback so that they can develop new ideas and new techniques and new reasoning processes. And that's why from the very beginning, AI, computer science, and games have been so intertwined. And so the story that I'm going to tell you here is just a continuation of that story, taking a game that was very, very hard for computers to reason about, seemed almost maybe impossible for computers to reason about, and seeing if we can now tackle that game and develop new ideas that will allow us to reason in those kinds of games. So what kind of game are we talking about? Well, that whole history that I laid out, every game I mentioned is of a particular form. They're of the forms of these sort of games. They're chess and checkers and tic-tac-toe and Go. And what these games are is they're called perfect information games. So perfect information games are games where you have all the information you need to make your decision at the time you have to make your decision. Like literally in most of these games, they're right there on the table in front of you. Everything you need to know is available. And in fact, you know that everybody else knows that because it's right there on the table in front of you. But that's not all the kinds of games in the world, right? Many situations that we decide, many of our decisions, that property isn't available to us. We have to make choices where we don't have all the information available. And in fact, in these early thoughts about games and AI and computers, that was part of the original thinking. So John von Neumann, when asked about chess, said, well, real life isn't like chess. Real life, it consists of bluffing, of little tactics of deception, of asking yourself, what is the other man going to think I mean to do? And that is what games are about in my theory. So von Neumann imagined a much richer space of decision-making than what you get in a game of chess. And what he actually imagined was, he imagined poker. And I'm not just making that up. He imagined poker because when he wrote his seminal book on game theory, there's a chapter entitled Poker and Bluffing. And much of the initial work into game theory was trying to figure out, why is bluffing even a part of this game? Where does it come from? And why do people do it? And does it make any sense? Or is it just a human foible? And so they wanted to try to understand the mathematics that might justify that. Okay, so to understand this talk, you don't need to know anything about poker, which is hopefully good for some of you. If you know something about poker, it'll be even better. But there will be a few moments where I'm going to need to explain a little bit about the game. And at those moments, I'm going to have Professor von Neumann will show up on the screen, and I'll tell you a little bit more about the game. So this is one of those moments. So how does poker work? So the way poker works is each player in the variant we're going to play is dealt 2 cards face down, and they can peek at them, and only they get to see them. And the other player also has 2 cards face down. And now what we're going to do is we're going to bet. We're going to make wagers as to who has the stronger pair of cards. But now, after we made some wagers, there's going to be more cards revealed, so the state of the game will change, and we'll make more wagers about now who has the best pair of cards. And only if we get to the end of the game, where everyone has matched everyone's wagers, will we flip over the cards and find out who won. And so this game is a game of imperfect information. I don't know the other player's cards, but yet I still need to act without knowing their cards. But I also know my opponent doesn't know my cards. And so I need to act in a way that makes sure I don't reveal my cards unnecessarily, because I might lose an advantage that way. But I still need to act under that reasoning. Okay, so that's the game of poker. Before we actually get into how AI can handle games like that, let me talk about how AI handles games that aren't like that. So I don't know how many of you are actually in artificial intelligence, but if you've studied artificial intelligence, I want you to think back to when you took an AI undergraduate class, and you probably had to implement some AI that handled some sort of game. You might have actually programmed a chess playing program. That's not particularly popular right now, but you might have done that. In my case, I actually had to write a program that played Connect 4. But you'd have to be old if that was the case. More likely, you probably wrote a program that played Pac-Man. But anyway, there's various assignments that you might have done. But invariably, in any of these cases, you wrote a particular algorithm. And what I want to do is remind you of what that algorithm looks like. Okay, so the way that algorithm worked was there was a space of decisions that you wanted to consider. You had an agent, and they could take some actions, and you were going to consider each action they could take. Now, if it's a game that involved some opponents, you had to consider what actions your opponent might respond with. And then you would think about how ways you could respond to each of those opponent responses, and so on. And you would try all these different possibilities until you got to the end of the game. And then you would know, did I win or did I lose? And then what you do is start backing those values up. You'd say, well, of course I'm going to take an action that leads to a win, and now I know that's a winning position to be in. My opponent's going to take actions that try to force me into a losing position, and I'm going to keep working my way back up until I find the best action to take at this moment in time. So that's great, except for most of the games, and the ones I presented there, are too big for you to actually do that reasoning in this space. The game's too big for you to see all the way to the end. So what you do is you don't look all the way to the end. You go back up to that short space where you can look a few moves ahead, because that's all you can afford to do. And then when you reach a decision that's only a few moves ahead, you don't know what the outcome is. It's not a win or a loss yet. You haven't won or lost yet. It's the middle of the game. So what you're going to do is take that decision, that situation, and you're going to evaluate it with some value function. So you're going to put it into some heuristic value function that says, this is how good it is to be in this situation. But now we do the same reasoning process. We'll just treat that. It says, oh, I think this is likely to be a win, so we'll just pretend like that's what's true about that situation. And then again, we'll back everything back up to make a decision. But now we make that choice in the world. So now we've taken that action, we've made that move on the board, my opponent now makes some response, and now I have to act again. So what do? Well, I'm just going to repeat that process again. But now, because I'm deeper into the game, I get to look further ahead before I'll run out of computation time. But also when I do that, I get to forget everything that came before. It doesn't matter how I arrived at this position, who moved which pieces to get me here. All that matters is I'm now at this board configuration, and I can start doing my search from that point onwards. But again, I'm going to reach some non-terminal states. I'll use my evaluation function to figure out how good it is to get there, and that will let me decide what action to take. My opponent will take some response, and then I'll repeat the search again, constantly getting further and further, deeper into the game, until I can eventually see all the way to the end, and then we'll get to the end of the game. Okay, hopefully that looks familiar to you, because that is like one of the most fundamental computer science algorithms we have. Right? So this idea of depth-limited search with an evaluation function appears everywhere. It's not only a part of our chess playing programs, it's not only a part of AlphaGo, it's a part of things like reinforcement learning. It's the fundamental building block of reinforcement learning. The idea that I only need a value function that will summarize all the future so that I don't actually need to reason through the future. I'll just look up values in this value function. It's also a critical part of path planning. It'll tell you I don't need to look all the way to the end to figure out if this is a good place to start moving down my paths. It's used in routing circuits across circuit boards so that we can actually find good paths of figuring out how to create PCBs. It's used everywhere. This is search with a limited depth is a fundamental algorithm of AI. And yet, we can't do any of that in poker. So while that's a fundamental algorithm, we have yet to, prior to DeepStack, had no idea how that would be applied in a game like poker. And there's a number of reasons why. Let me walk through why. First of all, you have to be able to search from the state you're in, but in the game of poker, I don't know what the state is that I'm in. I don't actually know what the other player's cards are. So when I think what action I'm going to take and I look at how my opponent might respond, I can't know how they're going to respond because I don't even know what cards they were dealt. So I actually can't start a search from a position where I don't know where I am. I have a second problem, that I can't actually forget what happened in the past. Because to forget what happened in the past is to forget how we got here. But how we got here tells me about what cards my opponent has. So if I saw them make a large bet, that's going to influence what I know about their cards. In fact, how we got here tells me about what my opponent knows about my cards. So if I've recently made a large bet, then that my opponent might know that I have good cards, or maybe I'm bluffing. So, but all of this process sort of fits in together. I can't actually forget how we got here. And even the last piece is bad too. I can't do the evaluation function because that presumes I give it a state and it tells me how good it is to be in that state. But I don't. But a state isn't defined as being like a particular position on the board, because now a state, in order to evaluate a state, I actually need to know things like what do everyone believes in this state. It's not enough to say what are the cards that I hold right now, because holding a pair of good cards, while that's really good and you want to hold a pair of good cards, it's even better to hold a pair of good cards when your opponent doesn't know you're holding good cards. It's much worse to hold good cards when your opponent knows you're holding good cards. So I need to account for in these evaluations functions somehow what my opponent knows about my cards from what I've revealed and how I've played. Okay, so we have some problems. So what did we do? What is the approach that we actually do in poker? Well, we actually did something very, very different than was done in perfect information games. What we actually do is we reasoned about the whole space at once. So we are actually going to look at the entire possibility of decisions and think about all of them. Now, the problem is, of course, the game is really big, and this was a problem for the perfect information case, which is why they didn't do that. But we have to, and it's because it allows us to make sure that how we play when we hold a certain set of cards, is like ace-ace, is related to how we play when we hold a jack and a queen, or a 2 and a 5, because those situations all matter. It matters how I play in those situations because it affects what my opponent could know about my cards and what I could know about my opponent's cards. So, but we do have a problem. We can't reason about the entire game, so instead we're going to take a sparse version of that tree. We're going to take the big tree, it's too big to think about, and we're going to just get rid of a whole bunch of things and pretend like they can't happen and they don't happen. So we're only going to take some subset of the paths through this tree, but then before we play the game, we're going to analyze that tree in its entirety and come up with how to play the game and write everything down in a big table before we even sit down to play. So we've resolved how we're going to play in every one of the situations in our sparse version of the game. Now, there's still some problems with doing this, which is, well, invariably when we sit down to actually play the game, something's going to happen that I didn't put in my sparse version of the tree. At some point, someone's going to take an action, or a card's going to get flipped over, and I didn't account for this when I created my sparse version of the tree. So I'm going to have to do something while I'm playing the game to figure out, I don't know what to do underneath that. That wasn't even something I thought could happen. So in order to act, what I'm going to do is I'm just going to pretend like that actually is in fact something else happened. Like I know that you bet 150, but I didn't even think you could bet 150, so I'm just going to pretend like you bet 100, because I know what to do when you bet 100. Okay, so that's now how I can play the game. And this idea is called abstraction. It takes a big game and abstracts it down to a smaller one that maybe I can reason in. And the way we handled poker was we actually would pre-compute a strategy to one of these abstractions before we sat down to play the game, and then we'd do this mapping while we played. Okay, this actually can work. So before I jump into Deep Stack, let me just make a brief foray into a previous program called Cepheus. Cepheus actually played the game of Heads Up, Limit, Hold'em. And its goal was to actually not just play the game of Heads Up, Limit, Hold'em. When we set out to do Cepheus, which was a couple years ago, we set out to solve the game of Heads Up, Limit, Hold'em. Heads Up, Limit, Hold'em is the smallest variant of poker that humans play. We're going to talk about Heads Up, No Limit in a minute, but this is the smallest variant that humans play. And over time, we had actually been producing programs that could solve very large versions of games. So we could solve abstractions increasingly larger and larger and larger as we improved with the algorithms. And so in 1993, we had the first In 1993, we had the first algorithm that could solve a game of imperfect information, like poker, in polynomial time. Up until that point, we didn't even actually know, like the largest games we could solve, we could only do by hand on paper. It was a disaster. So it was only in 1993 that we could finally get computers that could solve games with maybe 1 million decision points in it. We then had the computer poker competition start, which drove research dramatically, and we saw big jumps in the performance of how big of games we could solve. 2 order of magnitude improvements within a few years, now 4 order of magnitudes improvements. So we could solve games 10,000 times larger than previously possible. So what this means is that when you did your abstractions, you actually didn't have to abstract as much. You could actually now solve a bigger game, so you didn't have to put together too many situations as much as you did before. So in fact, at the time, we were mostly working towards heads-up limit. That's how big heads-up limit hold'em is. So it's a little bit higher than our capabilities of being able to solve games in 2013, but it was about 2 to 3 orders of magnitude away. Now, at the time, even at that moment, before we started Cepheus, it was in 2008 that we build a program that could beat professional players. So long before we could get to the level that we could actually solve a full game of heads-up limit hold'em, we could actually beat professional players by doing this abstraction idea, even though we were about 5 orders of magnitude away from being able to solve the game outright. Okay, but we wanted to set out to see if we could actually close this gap. Could we actually solve a game as large as heads-up limit? I need to make another stop here on our poker way. I need to explain how you measure performance in a game like poker. You don't win or lose poker hands. You actually win a certain amount of chips. And the amount of chips you win will determine what stakes you're playing for. You might be playing for $1,000. You might be playing for pennies. And strategically, that doesn't change the game. So we want to normalize for that. So we we do that around a big blind, which is just the stake level you're playing for. And then in order to make the units sensible, we talk about millibig blinds per game. All you need to know is it's a magical unit. It's a number that I'm going to use throughout the talk. But let me give you some benchmarks of what these numbers can mean. So if you were to fold every single hand without even looking at your cards, like you don't even pick them up, you just say, okay, I fold, I'll just give you the chips in front of me, then you'll actually lose by a rate of 750 millibig blinds per game. So that's the rate of a really dumb poker strategy that just folds all of its hands without even looking at them. A professional player, on the other hand, is trying to win at a rate of about 50 millibig blinds per game. So if they do that, they can actually sort of overcome the variance of the game. They can sort of be profitable if they can maintain a win rate of about 50. If we actually produce a perfect poker strategy, we would, of course, get 0. We wouldn't get 0. We would guarantee that we got 0, even no matter who we play against. And if someone we played against was making mistakes, then we would actually make even more than that. But we can actually guarantee, if we produce a perfect poker strategy, that we would never lose money no matter who we played against. And we know such a strategy exists. It's just computationally hard to compute one. One more number that you can't quite see on this chart is the number of 1. Suppose I wanted to produce a perfect poker strategy, but there's floating point errors and small approximation details, and I can't quite get to 0. Like, what if I got really, really close to 0? How close would I have to be before you could not tell that I wasn't playing perfect poker? So we actually calculated a number that would be how close you'd have to be where a lifetime of a human playing against the program could not statistically separate it from being perfect. And it turns out that number is 1. So if you're within 1 millibig blind, if you can guarantee you don't lose more than 1, no matter who you play against, then no human will ever be able to know whether you're not, in fact, playing a perfect game. Okay, so that's our goal. That was Cepheus's goal, to, in the game of heads-up limit, reach an exploitability of 1, which is to guarantee it can't lose more than that. So where were we? I showed that chart of being able to solve larger and larger games, but how does that affect our exploitability numbers? As we solve larger and larger games, so on the x-axis here, we have the size of game, the abstraction that we can solve. So as we get our abstraction bigger and bigger, we don't have to do this merging together anymore of disparate sets, disparate information states. And as you can see, the exploitability, of course, comes down as we do that. This is great. We're not having to put together strategically different situations as much anymore, and so we're less exploitable as a result. But there's a slight problem, and that is that if we keep going, you might just think, well, let's just keep solving a larger and larger abstraction, and eventually we'll get down to 1. Except this red line is showing you the size of heads-up limit hold'em. It isn't any bigger than that. So this abstraction game that we're playing isn't actually getting us closer to 1 than if we just outright solved the game. So in fact, abstraction seems to maybe be holding us back. And so that's what Cepheus was about. What if we could actually just chuck abstraction to the road, and we're just going to outright solve the game that has 10 to the 14 or a million billion decision points? So I'm not going to talk about the algorithm because I really would rather spend time on deep stack, but let me just show you what we ended up doing. This was a program that would learn to play the game of heads-up limit by playing against itself. And so this is over time. The x-axis is now time of it playing against itself. And this is going to show you the exploitability come down. We have 3 sort of benchmark lines here, which is the exploitability beating that of always folds. So that's a really naive strategy that loses 750 no matter who it plays against. This Polaris was the program that beat professional players. It actually was exploitable for about 280. And then the previous best known exploitable strategy was on the order of about 40. And so when we started running our computation, within the first 10 hours, now we did run this on 4,000 CPUs at once. In the first 10 hours, which now 5 CPU years has actually gone by, we actually reached the point that we were playing better than if it folded every hand. Very exciting. By the end of the day, roughly by the end of the day, we actually reached the point that we could now beat, we were less exploitable than the program that had beat professional players. And this had taken, and now it's used 16 CPU years, so it's a teenager. We keep running it, and now we're reaching its old age, 59 CPU years. It's ran for 4.5 days, and we're now crossing the barrier of the least exploitable strategy that had been known before. Now, of course, the problem with log-log plots is that this distance is going to take a long time, and it was excruciatingly long watching the program run and watching its exploitability fall. But 69 days of computation later, or 900 CPUs years later, it's now of a biblical age. It now reached the point that it was 0.986 exploitable, which is under our number 1. So we had reached the point that we had produced an essentially solved strategy for the game. But to do that, we had to kick abstraction to the curb. Okay, let me talk about DeepStack. So DeepStack is a game that plays heads-up, no-limit hold'em. So we'll go back to Professor Neumann to answer what's the difference. What's the difference in limit and no limit? So in limit, the way the wagering works is that someone will say, I bet. They don't give an amount because the amount is dictated by the game. So they'll just say, I bet the fixed amount of the game. The other player might say, okay, well, I'll raise your bet. And the raises are of a fixed amount, so they don't have to say an amount. And then maybe a player calls. In no limit, you can actually bet any number of the chips in front of you. And so someone might say, I bet 400. And the person might respond, okay, well, I'm going to raise you 8,192. They can make any bet. And that's a different bet than 8,193. So they can make any chip size they want to. And then, of course, you might have the sort of, from television, the iconic all-in. I'm going to put all my chips in and bet all the remaining chips that I have in front of me. And then the betting might call. Okay, so that's the difference between the game. The one game, you're forced, all your bet sizes are fixed amounts, and the other game, you can make any size bet you want to. Okay, so I gave this plot of how big of games we could solve, and we plotted heads-up limit hold'em on here. So let me show you where heads-up no limit hold'em sits on this graph. We're going to have to go up a little bit higher. Sorry, it's a little bit higher. Oh, there we go, okay. So there's 10 to the 160 decision points in the game of heads-up no limit hold'em. This is enormous, right? That's more than there are atoms in the universe. In fact, that's more than there are, if we put a universe inside of every atom, that's more than there are atoms in that. So this is a huge game. Now remember, we said we could actually beat pros at heads-up limit when we were only smushing together about 10,000 decision points. Like we had to find 10,000 decision points that were strategically enough the same that we could just pretend like they were identical. If we want to do this, we have to squeeze an entire universe inside of an atom, and then we have to do even more than that, right? Like we're going to put together whole universes together. This is a terrible idea. Like to illustrate how bad of an idea abstraction is for no limit, let me suggest how it would work for chess. Here's how we're going to play the game of chess. Oh, wow, that looks like a complicated game. There's a lot of pieces in that game. There's 10 to the 50 states in that game, decision points. That looks like a smaller game. I bet you I can figure out how to play that game. So we will. I'm gonna solve that game outright. I'm going to figure out how to make a move in every possible state of that game. And now I'm ready to play full-scale chess, right? So it's the first move of the game. What should I do? Well, in this other game, the first thing I might do is maybe I'll move my queen in front of my king. So, okay. I don't know. Like, what does that mean at all? It doesn't mean anything, right? Like, there's no way to turn a move in that smaller game into the bigger game because there just isn't anything strategically similar about it. And that's kind of what we've been doing historically in heads-up no limit when we applied abstraction techniques. Okay, so DeepStack is about kicking abstraction techniques out of the way of heads-up no limit as well too. But to do that, we're going to have to go back to this fundamental algorithm that we talked about at the beginning. How did we do this in perfect information games? Because we obviously don't do that in chess. And I mentioned that there were 3 problems with doing this fundamental algorithm, and DeepStack's going to overcome those 3 problems, and that's how we're going to get our solution, our algorithm for this game. So the first problem, just to remind you what they were, is we can't, we don't actually have a single state we're in when we're trying to do our reasoning, because it depends on what the other player's cards are. We also can't forget what came before, because that seems to tell us about what the other player's cards are and about what they know about my cards. And we also can't evaluate states independently of knowing what are the beliefs of the players involved in those states. Okay, so DeepStack's going to try to get around these 3 problems. And the first step is to think about how can we forget things. So let's suppose that the game has happened. We have played some decisions, and we've reached at some point in the game that we need to make some choices. We want to reason now on that smaller game that's just what's left over. Maybe we're really close to the end of the game. There's only a few more actions left, and we'll be out of chips, and someone's going to have to flip their cards over. So the first thing is we're not going to search from the actual decision point we're at. We're not just going to say, well, I have these cards, so what should I do next? We're going to think about all the cards that I could possibly have at this moment. And I'm going to think about all the cards the opponent could actually have. And I'm actually going to do my reasoning in that combined space. So even though I know I'm holding a certain set of cards, I'm actually going to reason about all the things that people don't know, because I need to capture their beliefs. But now I want to forget everything that came before, so I'm going to actually have to, but I also said I can't forget everything that came before, so I need to summarize it in some way. So the first step is, what do I actually need to remember about what came before? The first thing I need to remember is my range. So here I'm using the word range to just mean a probability distribution over the cards I could hold at the current moment. So at this point, I actually know this because I've actually played to get here. And I have a strategy, and so I could actually use my strategy and Bayes' rule to compute what other cards would I have played the same way and with what probability, and that gives me a posterior distribution on what cards I could hold. And with that range, that's the best the opponent could possibly know about my cards. If they knew every intimate detail of my strategy, that's the most they could understand about what I hold right now. Okay, so I'm going to use the past to summarize my range. The other piece of information you might think I would need is their range. Like, wouldn't it be nice to know their distribution of cards? But that's tricky because I don't know how they're going to play. So it turns out that I don't need to know their range necessarily. What I actually need to know is the value of them holding certain cards and what they could have done if they had it in order to not get here. So it's basically for every one of the cards they could hold, how much could they have gotten even if they hadn't reached this by taking some other actions up along the tree? If I know those values, then I can actually figure out what's going to motivate them. What cards do they want to bring to this sub-portion of the game? So it would take more detail to actually explain what's going on here, but I'm just going to leave it at the two things I need are my distribution and a set of values that correspond to what could the opponent get with each of their cards had they deviated from getting to here. Okay, once I have those two things, it turns out that's enough. I can actually forget everything that happened before. It doesn't matter how I got here. It doesn't matter what. There could be many, many different ways at play here. But if they gave me the same range and the same counterfactual values for my opponent, then I can play those two situations exactly the same. So now I can forget things. So that's a good start, but it's not everything. Because what about toward the beginning of the game? Let's suppose that I'm near the beginning of the game, and now I need to actually make a decision. I'm still having to search this enormous dark blue triangle to figure out how to play all the way to the end. Right? But we know how to, well, first we can forget things, that's great, but I still have this enormous dark blue triangle. So from perfect information games, we know what to do, which is we're not going to look all the way to the end of the game. We're only going to look a few actions ahead, and then we're going to apply some sort of evaluation function. But that was one of our problems. I can't evaluate single poker positions. I need to evaluate sets of them. And the reason I need to evaluate sets of them is because those sets need to incorporate the beliefs the players actually have. So when I'm going to do this evaluation, which I'm going to have a value function, it's actually going to take what if I reach this poker situation where I could be holding this distribution of cards and my opponent could be holding this distribution of cards. And that's what my value functions are going to sit on top of. And what these are they're holding the beliefs the players could have about the opponent's cards, each other's cards. Now, once I have that, this is now a small game. Now, I still need to think about this game theoretically. I don't apply a search in a traditional minimax way, if that's what you're thinking. We still have to use a game theoretic algorithm, but we can actually reason in this space and actually produce a strategy. And now I take an action, my opponent takes an action, and that's great. And now we're going to do exactly the perfect information thing. We're at some new decision point, and I need to act again. So now I'm going to reconstruct the search space that lets me look deeper. Now, there's one problem, though, that I don't have. I need to get the ranges and counterfactual values for this point here. And so I'm going to have to somehow move these down. And the first step is what happens after my action. For my action, it's easy. I can update my range with the Bayes rule, right? I know what action I'm going to take with each of my cards, and so I'll simply update my probability distribution given Bayes rule and what my probability is of taking each action. For the opponent counterfactual values, it turns out that counterfactual values are an intimate part of the algorithms that we use to solve even these small games. We're using a counterfactual regret minimization algorithm. The counterfactual values are sitting there right in the algorithm itself, and so we can actually just pull the values from there. When my opponent acts, though, my opponent can't change my range at all because that can't affect what possible distribution of cards that I hold, so I don't even have to do an update when my opponent acts. Now, for my opponent counterfactual values, they could change their counterfactual values based on their action, but only if they took a suboptimal action. Because I just actually solved the small decision problem over all possible distributions of cards that they could hold already. And so only if they were to take a suboptimal action would it go down. And what we're going to do is just not do the update there. Even if they took a different action, I'm just going to ignore that because it doesn't. All I need to do is have a bound on what they could have achieved, and I can still make a theoretical guarantee that our result is sound. Again, the whole counterfactual value is a detail that's too much to go into at this point. Okay, so now we can update the values, we can forget about what came before, and we have our complete procedure that, just like we could for perfect information games, we only look ahead a small number of actions, we use an evaluation function to summarize the entirety of the future, and we can take our action, constantly now redoing the reasoning every time we take a new action. We have that exact same thing for imperfect information games. Of course, there's a number of changes about how we represent situations in the game, what our value functions have to operate over, and what we have to maintain in order to forget the past. Now, the cool thing about this is not only do we have a heuristic evaluation function that can do depth-limited search, and we have a version of this canonical algorithm in computer science, not only do we have this for imperfect information games, it also means that 50 years of history of understanding how perfect information games can do search, there's a whole ton of ideas about where evaluation functions come from, how we should prune search, how we should push it. We now get to pull all of that over into imperfect information games. And we haven't even scratched the surface on what you can do there. DeepStack's going to pull over one idea that we've learned in perfect information, and that is about where this value function comes from. So recently we saw with AlphaGo that you can actually represent very, very powerful value functions, even in very complex spaces, using a deep neural network. And you can actually learn those value functions from feeding it in data, and so that's what we're going to do. We're going to we actually have a complex value function too. Our value function needs to take in beliefs about what cards you hold and what cards your opponent holds. That's what our value function has to do. These are going to be complicated, and so we're going to rely on deep networks to be able to represent that capacity that we need to. So whenever you do deep learning, you have to put a cool DeepNet picture up on the screen. So that's our DeepNet. This is slightly misleading because it looks like it's fancy, when really the reality is that most of the work is happening here in just 7 fully connected layers. This is, in fact, the most vanilla network that you could really produce. There is a little trick at the end that it's possible the deep network could produce values for poker situations which don't sum to 0. We actually know the 2 players must be a zero-sum game, and so we know the values have to sum to 0 weighted by their ranges. So what we actually do, even though the deep net isn't constrained to do that, we add a little gadget at the end that computes how they differ and subtracts off the difference. And so it always guarantees the output of the network is 0-sum. The nice thing about that is that's fully differentiable, so you can actually roll your gradients through the 0-sum part of that network as well too. So now what do we do? In order to train this representation, we are going to generate random poker situations. We're going to generate tens of millions of poker situations. Each one of those we'll solve ourselves, because they're now smaller poker situations. We'll solve them by playing against ourselves in that situation. We'll find how good it is to be in that situation, and then we'll throw that off to the deep network to actually learn a sort of intuition about how good it is to be in that particular poker situation. And if we've done a good job, if we've fed it enough situations, then we should be able to give it a new situation that it's never seen before, and it should be able to generalize what it's learned from other situations to be able to have an intuition about that new situation too. And that's what we need this to do to be able to use it to play. All right, I'm running out of time. I want to talk about evaluation. Evaluation turns out is really hard in poker. In fact, we spend almost, probably a quarter of all of our papers on AI and poker actually are more about how do you evaluate poker agents than it is about the actual building of them themselves. And part of the reason is because one of the things we want to do is approximate. Our goal here is to approximate perfect play. We're trying to get as close to this sort of Nash equilibrium as we can, one that guarantees we don't lose, that we're never making any mistakes. But in order to evaluate that, you actually have to measure your exploitability in the worst case. You have to be able to measure how bad could someone beat you if they knew every detail of your strategy. And in a game as large as Heads Up No Limit, you can't do that. So we wanted to try to see if we could approximate that anyway, and we developed this greedy technique that tries to compute a greedy best response. It's not a full best response, it's sort of more of a localized best response. And what it does is it gives you an idea of how exploitable a strategy is. It's only a lower bound. The strategy could be more exploitable than this number, but at least gives you a sense of how exploitable a strategy could actually be. So let me show you what you can do with this sort of greedy approximation of how exploitable a strategy is. So we ran it on a slew of strategies that are state-of-the-art as of 2016. These are top heads-up, no-limit computer poker programs. So first, actually, always fold is not one of those, or at least we don't usually think of it as. And we said that always fold, we know that it's going to lose by 750. We also know it can't lose by more than that because it never risks more than that. So the exploitability of the always fold strategy is 750, and local best response can find that, of course. And then we have 3 sort of state-of-the-art poker strategies, and they're beatable for 4 times as much as if they always folded. And I just said the always fold is a bad strategy. Well, it turns out it's not. It's actually better than all the other strategies we knew as of 2016 in terms of knowing how bad they could be beat. Basically, the best strategy we had as of a year ago to play the game of poker was to not look at your cards and just simply hand them the chips. You might think, if you know something about computer poker, you might think that has to do with betting abstraction. We wanted to try to normalize for that as well too. So we actually produced a strategy that doesn't actually have any betting abstraction at all. Let me get this straight here. You might have thought it had to do with card abstraction because all of those programs actually do card abstraction. We want to normalize for that, so we actually took a strategy that has perfect cards. It does no card abstraction at all. And still then, even in that case, it's actually exploitable for 3 times always fold. So it doesn't really matter which way you push these abstraction ideas. The problem is just that you're putting a whole universe inside of an atom, and that isn't going to work. If you actually take deep stack and run the same idea against it, it not only it can't find any flaws in deep stack's play, it actually is losing to deep stack. So this doesn't say that deep stack is perfect. It doesn't say that it's even less exploitable than these other strategies. It does say that you're going to need a much more sophisticated strategy than these sort of greedy look-ahead, one-step look-ahead ones. But it also means that its mistakes, it's hiding them much, much better than the previous techniques did. The other way to evaluate strategies is of course, to play them against other players and play them against humans, for example, who are known for being able to find flaws in how people play. Now, the tricky part of that is there's a lot of luck involved in a game of heads up, no limit. And in fact, that 50 millibig blind number, I said professional players want to beat their opponents by about 50. It actually takes about 100,000 hands before they can be statistically certain that they're actually winning, or statistically high probability that they're actually winning, even when they have a margin of that 50. So the only way professional poker players actually win at this game is they actually just play 1 million hands a year. Like, that's what they do. So if we're going to try to benchmark against players, we're going to need a lot of hands. And that's actually a problem because that requires them, we're going to have to get some human player to stay focused for that long, or we're going to have to pay them a lot of money to get their time for that long. And both of those are a problem. So we actually developed a technique, and I'm not going to describe it for the lack of time. We developed a technique called AIVAT, which it's very cool, but let me just give you the gist of what it actually does. What it does is it looks at the actual decisions that are made in a hand and separates your winnings on that hand. How much did it come from you getting lucky or unlucky, and how much did it come from you making skillful choices? And we can actually do that in an unbiased way. We can prove that, and so we can get an unbiased estimator of the same thing that money would get, but with much lower variance. And the sort of bottom line of this is that 3,000 hands using this technique called AIVAT is about the statistical equivalence of 90,000 hands of playing, just looking at how the money changes hands. So this is great. It now means we can actually have a chance of running our program against poker players and finding out who's better. And so that's what we did. Last November, we recruited 33 poker professional players. We gave them 4 weeks to play 3,000 hands, so they'd have lots of time to be able to take breaks as they needed, play as they wanted. To give you an idea of some of the players, one of the players is Phil Locke. He's won $3.5 million of live winnings playing poker. He also has a World Series of Poker bracelet. So he's a very accomplished poker player. The results of playing against those players are sort of densely shown on this graph. Each of the players is one of these columns. So we had 33 participants. They're sort of ordered such that the players who played all 3,000 hands are listed first. So not all the players actually played all the hands. So the players that did finish, we listed those first, and then everybody else is listed by how many hands they actually completed. So the first thing to note is this red line is showing you the line at which deep stack, so anything above that red line means that deep stack was actually beating that player. And so we only saw 2 players for which were actually below the red line for deep stack, but the confidence interval is also, they only played less than 300 hands, so there's no way that that number is statistically significant. And Anyone who actually played more than 300 hands is not only behind deepstack in terms of beating it, but it's actually losing to deepstack by more than that 50 number that professional players want to win by. And we're doing that against other professional players. You might wonder why not everyone played all their hands. Well, there are some players like this player here whose dot isn't even on here, who might have been discouraged about some initial choices that they made and decided that maybe now's the time to stop playing. And so many players were actually losing by more than the 750 number that's always fold, which means they should have just not even bothered looking at their cards. The actual number that we were winning by is 486 over all the hands that were played. So that number is, again, sort of close to 10 times the numbers that a professional player wants to win by. Even amongst the players who finish their hands, that number is still almost 8 times what the professional players want to win by. Lastly, you might care where Phil Locke, this is our accomplished poker player, poker professional, he's only in the middle of the pack of the 11 players who actually finished the 3,000 hands. The other cool thing about deepstack is by only having to do this depth-limited search, it doesn't have a massive computation. So after we've trained the neural network, it can actually play on a single GPU, and it can just run on a gaming laptop. And it still takes actions in about 3 seconds per action, or about 7 seconds is all the thinking time it needs per hands, which puts it right in the ballpark, or even faster than most humans play. It's also cool because this depth-limited search means that most of its reasoning about the game happens while it's playing, which means we can actually take changes to the game. We can actually change how the game works, and it can still actually figure out how to play that game. Now, its heuristic evaluation functions might be a little bit off because its sort of intuition was trained in a different game, but it can actually play, and in many cases it can play well. So one of the things we can do is have it play any stack size instead of just the one it trained on. And that also means that we can do freeze-out tournaments, which is much more like how humans actually play the game of heads-up no limit. In the study, what we actually did was after every hand, we just reset the stacks so that everyone had the same number of chips in front of them. But really, when you play a game of no limit hold'em, when you actually, if I take half your chips on the next hand, you have to play with half as many chips. That's just the way the game works. And deepstack can play in that format. And in fact, one of the things that we've started to do is we've started weekly live matches of deepstack versus the world. We're going to recruit various poker players from around the world to try their hand at playing freeze-out tournaments against deepstack. I have an error on the next slide here. It didn't actually start today at 11 p.m. It actually started yesterday at 11 p.m. So you missed the first match of deepstack versus the world. But every Wednesday, the start time might vary depending on the player's availability. But next Wednesday, I forget the start time. I think it might be 2 hours earlier, I think. So it might be at 9 p.m. here, local time. The result of our first match is we won 3 of the freeze-outs and lost 2. So that's exciting. If you want to follow any of the matches that we do or new results coming out of deepstack, you can follow us on Twitter or check out our webpage. Let me wrap up by just reiterating that I got to work with the most awesome team I've ever gotten to work with. These 10 guys are great, and these 3 guys from Czech are the best as well, too. And I'm super honored that I got to spend a year with them. Thank you for letting me borrow them. And if you have any questions, I'm happy to take them. So deepstack actually reasons, so at every decision point along the way, it's going to do a little reasoning process, right? That little look-ahead tree. So at the beginning of the game, its ranges start where it's just uniform, right? Like it knows its range. It's dealt 1 of 2 random cards. No. So deepstack now reasons about when it's making its first action. It thinks about how it's going to play with every pair of cards it could possibly hold, not just the ones it actually is holding. And then it can actually update its range in real, like it just updates its range. It says, what other cards would I play the same way? And then it updates its range to match that. So its range is in fact correct with how it actually plays because it actually reasons about every pair of cards it could hold. So it's actually, we're not feeding in the correct range that imagine it holds, nor is it tied to some sort of human-like performance. It's actually pulling it from this is how I actually play. Yep. More questions? Yeah. Right. So in fact, the space that it has to respond to is actually like a continuous space, because it actually needs to. The inputs into the deep net are beliefs about the opponent's cards. It's actually a probability distribution about the opponent's cards, and a probability distribution about its own cards. And then it needs to know the pot size and any board cards that have been flipped over. And that's the input into the neural network. And from that, it has to say, if you were to play out the rest of the game from here, how much money do you think you would win with each of the pair of cards that you would hold? And so you might think that holding like a pair of aces, and let's suppose there's an ace on the board, so I have trip aces, this is great. Like you might think it has high value, but it actually depends upon, of course, the opponent's cards, right? Maybe the opponent's likely to be holding the full house here or something like that. So I need to look at the opponent's distribution to figure out how good it is to hold aces. But it also depends on what other cards I could be holding. Because if he knows I'm holding aces, if that's the only thing I could be holding right here, then he's just going to fold to my bet, and the hand's going to be over, and I'm not going to make a lot of money. But if he thinks I'm actually holding rags at this point, then the chance, the slim probability I'm holding aces, that's worth a whole lot, and now I'm going to make a lot of money. So those beliefs are critical to what the deep net has to learn. But you were asking about actions. It doesn't figure out how to. Yeah, go ahead. Yep. Yeah, so the deep net really does actually answer how to play, even in settings that you would never actually experience. And some of the things we probably feed it on the training data are of that sort. It's actually important that it does that. This is sort of not talked, I didn't really go into detail in this talk, but when it's solving that small look-ahead game, it actually has to solve it iteratively. It starts off by saying, I'm going to play randomly in this small iterative game. It then thinks, oh, okay, if I play randomly, then this is my values of all my actions, and so it updates its strategy, so now it's not playing randomly. It also knows the opponent's not playing randomly. It's constantly going back and forth, so when it runs those evaluation functions at the bottom, it actually keeps running them over and over and over again with different beliefs as it learns to play just that tiny little subgame. And so it actually needs to know how to play situations that never actually arise in the game so that it can learn what are the situations that actually do. Because it almost resolves for how to play from scratch every time it sits down, every time it makes an action. The only reason that's feasible is because it doesn't have to do that all the way to the end of the game. It always sees the game as being really small, even though the game is immense, because the neural networks summarize all that future complexity. Does that help? More questions? In the front, and in the middle, and the back. Yes? Yeah. So this is
another question.
Yeah.
So does it somehow take into account the player it is playing against?
Right.
Trying to create some kind of strategy or something like that?
Let me answer your questions in the opposite order. So DeepStack does not do any opponent modeling, as it's traditionally called. It's trying to approximate the game theoretic equilibrium of the game. We've done actually quite a bit of work on opponent modeling. Often that work is not nearly as successful as our game theoretic approximation work. So typically the best programs don't actually involve any opponent modeling now. I think the reason for that is mostly because we're trying to take on the best players in the world. They don't tend to make mistakes that are easily identifiable in a short number of hands. And therefore, it's hard to build something that in over a finite period of time we might play against a human over only 3,000 hands that we would be able to find mistakes at the level that they make. They certainly make them, but they're going to be more subtle than you could pick up in 3,000 hands, especially the best players. Now, your second question is, what happens if we play against weaker players? You might think, oh, well, like you're assuming I'm going to make good moves, so I'm just going to act randomly, and then you're going to have no idea what I'm doing. And the one thing that DeepStack guarantees is that that's only going to hurt you, right? And it comes out of the fact that it's a two-player zero-sum game. So if you want to deviate from playing perfect, then you're right. I might not conclude the right counterfactual values that you actually hold at this moment. I only have a bound on them, but the bound guarantees that I won't make any mistakes no matter how you play. And so we have if our neural networks are in fact close to optimal, like if somehow we could get them to, it exactly knows the value, so that then this would actually be a perfect strategy, and it doesn't matter who you play against, you're not going to beat it. Now, with that said, it doesn't mean that I'm going to exploit you for all your worth. Like, you could be a very, very bad player, and maybe I'm only going to beat you for 300, and someone else could beat you for 800. DeepStack won't maximally exploit bad players. But it's not going to lose just because you're playing not the best poker. In the middle, yeah. So, yeah, so in a more than 2-player game, there's 2 issues. One is the theoretical ones. So like a lot of this is a very well-grounded, there's a whole theory behind this. Like this theoretically is well-grounded in terms of what it can do. And as long as the neural networks can accurately produce values, then we can guarantee how close of an approximation you actually get. Once you go to the multiplayer game, we lose all sorts of, all this theory relies on certain properties of a 2-player zero-sum game that doesn't exist in a 3-player game. So all the theory is just going to collapse. But the algorithms still run. They actually still produce strategies. And in practice, those strategies turn out to look good. So not only have they won against other computer poker strategies, humans have looked at them and they actually think they're smart. In the smaller games. So like in a heads-up limit game, if you were to look at a multiplayer limit strategy, they're actually pretty reasonable, and the human players actually think that they're quite good. And many human players are actually using them to train from, even when we don't have any theory for what they are. I suspect that if you were to take DeepStack, which can cope with, because one of the problems of going to multiplayer is also the decision space explodes. So again, you go to the number of decision points gets even higher than 10 to the 160. But DeepStack doesn't care, because DeepStack never has to look very far ahead, right? It always sees a small game, regardless of how big the game is. And so I think that if you combine the fact that the previous algorithms actually produce good strategies, even when theory says they won't, with DeepStack's ability to not have to do abstraction and still see a small game, that I think there's a small amount of work to be done, but I bet you it's 1 to 2 years away from seeing a program like DeepStack being able to win at multiplayer games, pretty much any variant of poker that people play, because I haven't seen one that isn't susceptible to just taking it down with these neural networks. Yeah. Yeah, sorry, I think it was someone in the back. We're going to go back to you. I forgot. No, go ahead. Jump in, and then we'll jump to the back. So multiplayer games might be what's next. I personally can't decide, like someone's going to do this, and I can't decide if I want it to be me or if I'm just going to let it be somebody else. I'm actually really intrigued by other problems. So I think I don't want to say we've addressed the problem of how to make decisions when you don't have all the information, but we certainly have a new paradigm that I think can be pushed a long way in being able to make decisions in these imperfect information spaces. There are other challenges that we have, like the multiplayer one I think is an important one. But there's another one, which is how do we have agents and programs that can make choices when the rules of the game aren't entirely known? So, AlphaGo and DeepStack, they both know they're playing a game, right? They both know they're playing Go, and they know how the rules to Go work. They know that the deck has 52 cards in it. They know it's shuffled. They know what cards beat what other cards. How would you play this game if you didn't know that? And you actually, so humans aren't terrible at this. We go out our daily lives and we can make decisions all the time when we're not fully certain what the space of possibilities are in a game. And we just learn from it as we continue to interact in the world. And so I've done some past work on Atari games. So I sort of started this using Atari games to benchmark reinforcement learning algorithms, which gets at that a little bit. Like, can we actually build agents that don't know how to play an Atari game but can learn to play it through experience? I think if we could do something like that generally, and we could combine that with like these imperfect information settings and be able to do multiplayer, now we have a system that can make decisions when it doesn't have all the information. There's a lot of actors in the world, and it doesn't even know the rules of the game. If we can get there, we're darn close to the AI goal. In the back, yes. It's more like the latter. We would generate a random poker situation that really, there was some, we defined a distribution to those poker situations to make them look a little bit close to the kinds of things like the pot sizes that might exist in a real game. But we generated a random poker situation, and then we had one of our older techniques for solving, because now these situations are smaller. We took one of the older techniques for solving one of those, which actually does involve playing against itself. So essentially, it took that poker situation and then played thousands of games against itself, figured out how to play in that poker situation, but not for the purpose of remembering how to play, but for the purpose of figuring out how valuable is it to get there. And then that became the input. That was the target value for the neural network. And so then it would train on that instance, but we wouldn't keep the strategy around. We only cared about the value of reaching that poker situation. So the way it actually worked, though, is we did that for a bunch of river situations, so situations where there's only one round to go. This is small enough that we can actually solve. And then we'd use that neural network to actually train situations that have 2 rounds to go by now only looking ahead 1 round and then using our trained neural network. So we sort of bootstrapped up its knowledge. So it knows how to play situations where the game's almost over, and we can use that to now play situations that are a little bit further away. And now if we needed to, in this case we didn't need to, but if we needed to, we could keep going backwards and now saying, well, now let's learn situations that are even a step further away from that, and we can keep bootstrapping our way back. Yeah? Right. So first of all, the neural network doesn't give you what you should do. It actually tells you what the value of holding certain cards in certain situations are. So to turn that into what actions to take, you'd essentially be following, you'd actually run deep stack. You'd actually run the procedure for how to play. How to turn that into rules, I think, is an interesting question, and I think it's an entirely open question. And I don't think this is unique to deep stack either. I think this is a problem that AlphaGo has too. Right? If you were to ask AlphaGo, why did you make move 39? I think that was the move that got everyone excited in the third game. You ask it, why did you make that move? And AlphaGo would just be like, I don't know, I win more when I make that move. And you just be like, thanks, AlphaGo, that was helpful. And deep stack's no different, right? Like deep stack would just be, well, because I'd lose money if I didn't do that. And it never gives you any informative answer to anything. And of course, that's somehow uncompelling, right? Like if you were to ask a strong Go player, why did you make that move? They would probably blather on for like 2 hours on why they made that move. And they could show you different lines of play and all kinds of stuff about why they made that move. And so it's a little, like I think that's an open area that we need to see AI improve. Sometimes this goes under explainable AI, but I think it's going to be important for us to have our systems be able to communicate back to humans about why they made their decisions, both because we want to understand what they're doing, but another reason is because we want to learn from them, right? We want to become better at making decisions from seeing what they do. Now, let me just end by saying that doesn't mean that we can't learn from DeepStack and we can't learn from AlphaGo, because we can, and it's already happening. Computers are already being used for humans to train from. While they don't get explanations for why these are the right decisions, just from observing them, it forces the humans to think in a different way. And often they come up with the explanations themselves. It'd be nicer if the computers could communicate them, but right now what ends up happening is that humans can actually play against these programs, and they get better by doing that. And we've seen that happen with older programs and heads-up limit, and I think we're seeing that happen already with no limit. Just last night, one of the players who was playing in the stream event was actually looking at each of the decisions and even said, every time DeepStack makes an unusual move, I'm not criticizing it, I'm thinking, what has it learned about poker that I don't know yet? Yeah. We haven't done any of that. I have to think about the heuristic values. Yeah, so mostly the way we set the depth of the search was out of convenience. We set it to go to the beginning of the next round. And this has a nice property that means that you actually don't, at the beginning of the round, you're never facing a bet. And so the neural networks never have to look up situations where they're facing a bet, which just simplified their learning problem. It shouldn't be hard to put in the other thing, but then we have to train that situation as well too. So one of the reasons it's not easy for us to explore that choice, because we'd have to train a new neural network that knew about bets faced. And so I think that's an interesting thing to do, because it would help us. Like one of the questions we get a lot is, well, that's great. You only use a GPU. What happens if you used 5 GPUs? Like, how much better would it be? And it's tricky because the way it's set up, we can't really necessarily search much deeper because, or finely tune the depth of the search in the way you would with a perfect information, because we're only doing it based on at the end at certain fixed points in the round. But I think that's an area that we're going to play with more now that we've overcome this milestone. Yeah. Yeah, there's an easy way to do that. There's probably 2 ways to do that just off the top of my head that would be easy. Now, would they produce, the question would still be, would they produce interesting fallible play? Like, would they produce mistakes that humans would find like exciting to train against when they're still learning? And I don't know the answer to that. But the 2 ideas are, one is when it's doing its reasoning, in that small subgame, it actually does it iteratively. Again, it plays against itself in that small subgame over and over and over again. You could actually just vary how many iterations it uses. Like if you set it to 0, it'll play randomly, which is of course not very interesting. But if you only did 10 or 20 iterations, it's like it's doing 10 or 20 sort of like thinking about what would you do if I did this. And so it would limit how close it is to being optimal. Maybe that would be interesting. The other thing you could do is take the neural network and just corrupt its values. And so you're basically breaking its intuition so it doesn't quite understand how the game works. We haven't tried either of these to know if they would obviously degrade DeepStack's play, and if you were to do that and played it against DeepStack, it would start losing. Whether that would be an interesting thing to play against for different skill levels, we haven't tried. In the back, yeah. No. We are going to release code of DeepStack playing in a toy poker game called Leduc Hold'em, not in the full game of Heads Up No Limit. There's maybe obvious reasons that we're not releasing it, but I'll iterate them anyway. We actually did release the source code to Cepheus. So the program that plays Heads Up Limit, we actually released the code. It plays the game perfectly, but we released it because as of 2015, no one was competitively playing this game. Like you could not go online and play it for any stakes that mattered. You could play only for pennies. And so the idea that I would have my programs playing online and taking other people's money, I find unattractive, and so I don't want to see that happen. Secondly, with Cepheus, it also required 1,000 CPU years, even if you had the code, before you could actually get it to play good poker, which most people don't have in their basement. Unfortunately for DeepStack, not only is this a game that's currently being played at like 500 or 1,000, like lots of money's going around in Heads Up No Limit, but also lots of people have a GPU sitting in their basement. So to release the code would almost certainly see people losing money to my program, and I don't want that to happen. And also, I think this is really, it's like the fact that poker is about gambling is something that, that isn't something that makes me excited about it. I think this is a scientifically interesting problem, and I don't want the science to be corrupted by the gambling elements. In the black and then in the blue. Nothing. And stuff. That's not true. There are problems to get this. Like the DeepStack in Leduc won't have to deal with some of the complexities of the full game. You know, is that insurmountable? I don't know. I mean, the minute we publish any of our algorithms, sure, someone can go do them for nefarious purposes. And there's always a balance there, right? Like we want to advance science by releasing code because it means other people can build on it. We don't want to put out code that just serves the purpose of allowing people to do bad things. Our goal with releasing the code for DeepStack Leduc is to try to balance that, to say, I think this sort of minimizes someone who doesn't know what they're doing from using it in the full game. At the same time, does it help the people who knew what they were doing? I mean, they probably could have done it from the algorithm description anyway. I mean, the pseudocode's in the paper. So, it's a hard trade-off to get right, but this is our attempt to balance pushing science forward without having bad things happen. Did you have a question? No, I mean, so most of these solvers are actually just using the academic techniques that have already been like published in the literature. Like that's what they do, is they go and they mine the academic techniques and then they go and publish, put them in their programs and sell them. I will say that people aren't treating them properly for what they are, right? You put in ranges and then it comes up with solutions, but it turns out that theoretically that's unsound. So I briefly mentioned that we need our range and the opponent counterfactual values. It's actually really important. You cannot do it with my range and my opponent's range. If you actually solve that game, and then you were to take another subgame and you solve that one, these two things are not compatible. They don't actually together mesh well to create a well-balanced strategy. And so there's something slightly wrong. Like I think it's probably, the fact that they're useful and humans are finding them useful just shows you how bad humans are at this game. Because these solvers are actually not suggesting the right thing. Oh yeah, I know. Yeah, I'm just saying that there's flaws in what they're doing because of that. Their play is not meshing well, and they're not actually necessarily getting closer to equilibrium play doing it. Well, with the exception that maybe they were so far away from equilibrium play that, moving north will move you both to magnetic north and the North Pole until you get close enough, and then they stop. Yeah. Yeah, it was, so we did fully connected layers because that was the easiest thing to do. I actually don't know. I think you guys started with ReLUs, right? And then you added preludes, and it got better. And then what was the only other decision we made was how many layers, and it was just like keep doing it until the training error doesn't go down, or sorry, the validation error doesn't go down, right? So there really wasn't anything fancy in that decision. Yeah, so once we gathered the training data, then it was just run it on the training data, try it with like we started increasing the number of layers. Hey, it gets better. You jump to 7, and it was like 8 isn't getting any better. Okay, we'll stop. Yeah. So when we did. So when we did our study, we played the variant of poker called Doyle's game, which is used in the computer poker competition. The way this variant works is each side has 200 big blinds in front of them, and at the end of the hand, it doesn't matter what you've lost or won, you get reset to 200 big blinds in front of you. So let me come back to that. The nice property of this game is statistically it means each hand is independent, which is great when you're trying to publish results. But it's not, again, how humans typically play the game, right? Their stacks constantly vary. And so the freeze-out tournaments that we're doing now is really exploring your question. So now when it plays, if it loses half its chips on the first hand, on the next hand it's got to play with half as many chips, which means the effective stack size is now 100. And so it's having to play with any stack size. We actually still only are using the neural networks trained with 200 big blinds as the stack size. So the fact that it's playing well is suggesting that it's actually the intuition you get from different stack sizes can help you as long as you're searching the space, right? Like you can't pretend like the game is 200 when it's actually 100 because you'll make a bet that's illegal, or you'll think you could make that bet, or you're worried about your opponent making that bet and you'll get it all wrong. But that isn't what DeepStack's doing. DeepStack is still reasoning correctly about its next few actions. It's just that it's valuing the future as if the stacks would go up to 200 big blinds. And so when it gets there, it now knows that, nope, it's not a 200 big blind game. And so it's always pushing its errors farther and farther away, which means that it can keep its mistakes far away. Any more questions? I'm sorry, say that one more time.
If it's like a free bet.
Oh, gotcha.
I can go onto your site and download it and play against it.
No. So the download is back to the question about we don't want people to use it. It's possible that for Cepheus you could sit down even though we let people also download the code, we let people sit down and play against it. For DeepStack at the moment we're not doing that. Partially is that it does take a GPU to run. So if I had 1,000, 10,000 people all playing it, I would have to have 1,000 to 10,000 GPUs running to support them. Also, part of it is that we still want to play around with running competitions against some good players, and then at some point maybe we'll allow more people to play against it, but we haven't decided when yet. Yeah. Yeah, so Lebradas also, while our paper was under review at Science, Lebradas did a match against some top heads-up no-limit players, and won as well too, which was an awesome achievement. There is some similarities and differences in the algorithm. So I think we were both caught off. I mean, we both weren't caught off guard. We knew we were racing to do this. But I think the timing, it was coincidental that the timing was so close to happening roughly at the same time. But we both independently developed one core idea that is important to both of them. We called it this continuous resolving. They called it nested endgame solving. This is the idea of that you can actually like solve the end of the game while forgetting what came before. There's a key difference between them, and that is where the neural networks come in, is they can only use their nested endgame solving when they're near the end of the game, because they actually have to look ahead all the way to the end. Our neural networks, by using this idea of intuition to cut off the future, means that we don't actually have to look all the way to the end, so we actually do our continuous resolving for every decision along the way. So because of that, in the early rounds, they can't actually do this continuous resolving, which means they still have to resort to abstraction. Now, they have other mechanisms, like overnight when they were playing against their players, they would patch holes that the players found in their abstraction with some overnight processes. So they had to do some things to try to fix up the fact that abstraction has problems with it. But it appears that they could do enough to push that older technology to actually be able to beat human players, which is pretty cool. I'm much more excited about what this means for the science of going forward. Right? Ours runs on a GPU. They had to run theirs on about 1,000 CPUs running at the same time. There's this whole supercomputer behind it. And this, like, the sky's the limit for what we can do here when we start throwing computation at it. I thought I saw one more hand. Yeah. I mean, I don't have a great answer to your question, but I actually thought you were going to go a different direction. Let me actually pretend like you asked a different question. But I'll still answer yours. But a pro player, to be honest, a pro player isn't actually trying to play really good poker. Like, this sounds a little odd, but it's not actually like a chess player. A chess player is trying to play a near perfect game, and a chess player would love to be able to like go up against the best player in the world and beat them. And in fact, they're honing their game to be able to do that. Poker players aren't doing that. Poker players are actually trying to figure out how to take money from really bad players who have too much of it. That's the way the whole system works. And so it's all about exploiting bad players. And in fact, some of the best players in the world don't even play against each other, right? Which is a total oddity from every other game. Like, the best players in the world at Go, they play against each other. That's what you do. In fact, you don't get to sit down and play against a good Go player if you're not a good Go player. Whereas in poker, that's about the only thing you get to do. If you're a good poker player, you don't get to sit down against another good poker player, because to do so would just be to like break even and let the casino take the rake and you lose money. Both sides lose money. So it's a little bit weird. Their games are more about trying to find flaws. Now, that's not true for everybody. There's a movement in the last 2 to 3 years where people are trying to become more game theoretically optimal, mainly because I think they think that's a better way to beat, again, the bad players, not because they think that it's going to be important for playing against other good poker players. But that's one thing that's true. So, and in fact, in that game, if you want to beat crappy players, DeepStack's not particularly good at that. Like, it won't lose to them, but it's not going to take them. It's bad at taking bad players' money. So yeah, I mean, it won't lose to them, but it's not designed to do that. And the best poker players, that's exactly what they're designed to do. So we're not testing them at what they're good at, and that's a criticism that's true. But that's also just a fact of how the poker ecosystem exists. Your question, though, was how do we know that they were trying? We don't. There were some small incentives to try to get them to incentivize them to make it worth their time. The same thing that CMU did, put up a little bit of money to make it worth their time. But in the end, I think the reason I'm not too worried about that is because I still think when it comes down to it, when poker players play, there's still a huge amount of pride on the line. It doesn't matter what hands they're playing. they're going to play to look good. We told them we were going to announce the results. We told them that their rankings are going to be known. And we told them that every hand was going to be published when it was all over with. So I'm sure that they did not want to look bad at those hands that get published, regardless of what was motivating them to play well. There had to be one last question. It was required, yeah. How large is it? Uh-oh. 1,000 nodes? 500. 500 nodes at each layer. 7 layers. Right, so that means there's like 2,500 weights between each layer and then 6 layers. So there's like on the order of whatever, 15,000 weights. What's that? That's right. The training actually happened on a GPU. The much harder part of the training is not actually training the neural network. It's actually gathering the data to do the training, because that actually involves playing out the poker situation to determine its value first. So most of our time, like there was computation before we played, about 150 CPU years of computation was done in order to build up the training data, and then a few days on the GPU was all that was needed to do the training.